Okay, so welcome to this next video in which we're talking about the intracellular domain of the Cys-Loop receptors, or the Cys-Loop ligandated ion channels. So, I've previously drawn this picture for you here, where I've drawn a very simple sort of cylinder representing the whole receptor. In fact, the structure is slightly more complicated than that. If we actually look at what we have, let me try and draw this. Okay, so shall I try and draw it? I will try and draw it. Okay, so I'll draw a nice big picture. So here is our receptor again. Okay, our Cys-Loop ligandated ion channel. And this is the portion that spans the membrane. And then you have the extracellular portion up here, which is interacting with the ligand. Okay, and then beneath it, what you have is a portion known as the intracellular domain. And in fact, I will just draw the subunit composition of these before I draw the intracellular domain. Okay, right. So here are these 5 subunits making up the Cys-Loop ligandated ion channel. Now, each one of these produces a little loop, okay, downwards, like so. So this one also produces a loop. So each one of these subunits produces a little loop that comes in, known as the intracellular loop. And I haven't drawn this as well as I hoped, because what's going to happen is all of these cis loops are going to converge on one another at the center. So basically, you've got 5 subunits, so you're going to have 5 cis loops. So if I draw it as though I'm looking from the bottom now, so I'm going to look from the bottom, then what I'll have, basically, is if this is one cis loop, one of these intracellular loops, then I'll have another intracellular loop here, another one here, okay, another one here, and another one here. So they all converge right at the bottom there. So really, I should have drawn it more like this. Okay, so I've only shown 3 here, but there would be 2 more coming from the back. Maybe 1 there, and also 1 there. 1 from each subunit, basically. So let me add some colour on this to try and repair the damage that I've done. Okay, so here is 1. Okay, this is the one from this subunit here. I should have colour-coded it, in fact, never mind. Here's another one from this subunit here. Okay, and they're forming this sort of hanging basket network where you've got these holes in between. So let me colour this in again. So here's this viewed from the bottom now. Okay, so we've got all these intracellular loops, as they're called, coming in and sort of making this meshwork where you have these holes coming out the bottom. So you're going to have the rest of the receptor sitting above here. So let me sort of circle around the rest of the receptor. And what you've got then is these sort of holes between these intracellular loops, okay, where you can gain access to the space within. And it's by going into the space within that you can then gain access to the pore that goes all the way through the receptor. Okay, so these little holes are known as portals. Okay, right, and those are the portals through which the ions must move. Okay, so now I'll label up these loops. So these are the intracellular loops. Now I need to show you on this membrane spanning topology picture that we had up here, where is the actual intracellular loop, and I'll show you that in a moment. So these are the intracellular loops, and when I show you where it is, it will then motivate the other name for these intracellular loops. So basically, in fact, I'll draw another picture of it down here. If we look at the membrane spanning topology of just one of these subunits, then we've seen that it looks kind of like this. It has this cis loop here. Here's the amino terminus, then the cis loop, then the first membrane spanning domain, the second membrane spanning domain, the third membrane spanning domain, and then what I didn't show on the previous picture, and this is why I've had to redraw it, is that you have this larger loop between the M3 and the M4 domain, and this is our intracellular loop that each one of these subunits produces. So it's a loop between M3 and M4, those 2 membrane spanning alpha helices. So this intracellular loop is also often referred to as the M3-M4 loop. Okay, and it's because it's between these 2 membrane spanning alpha helices M3 and M4. Okay, so each one of these subunits has this intracellular loop projecting downwards, and all of the intracellular loops come together at the bottom of the receptor to form this sort of alternating space where there's nothing, and then there's a loop, then there's nothing again. So what you have effectively is like a hanging basket. So if I draw a bowl, it's effectively like a bowl with holes in it. Okay, that's the way you should think of this. It's a bowl with these holes in it, and these holes are what I've called portals. So you're going to have these 5 portals, 1, 2, 3, 4, 5. So there's 3 on there now. Okay, so that's the way you should think of the intracellular domain. You should think of it as being this hanging basket with 5 holes in it. Now, what's the significance of this intracellular domain, as it's called? So this is the ICD. Okay, well, the significance of it is that when ions move through the Cys-Loop receptor, so for instance, let's take as our example the nicotinic acetylcholine receptor, the archetypal example of a Cys-Loop ligand-gated ion channel. Okay, so when the nicotinic acetylcholine receptor opens, it's going to allow sodium and potassium to move through it. Now, because of the electrical potential difference that is usually across the cell membrane, so let me just show this down here. So let's say this is the membrane in which our nicotinic acetylcholine receptor, which I'll draw very simply as just 2 bars like that, is sitting in. Then usually the extracellular concentration of sodium is 145 millimolar, and the intracellular concentration of sodium is 12 millimolar. Compare that to the concentration gradient of potassium. The extracellular concentration of potassium is 4 millimolar, and the intracellular concentration of potassium is 155 millimolar. So there's a concentration gradient favoring the movement of sodium inwards and potassium outwards. However, you also have to factor in the electrical potential difference across the membrane, which is usually somewhere around negative 65 millivolts, which means that the intracellular compartment has a lower electrical potential by around 65 millivolts than the extracellular compartment. Now, both sodium and potassium have a positive charge, so they want to be where the electrical potential is lower, which in this case is the intracellular compartment. So they're both going to want to be on the intracellular compartment. So in the case of sodium, the electrical potential difference across the membrane is potentiating the concentration gradient. So it's going to make the movement of sodium in bigger, whereas it's going to be opposing the movement of potassium out. So it's going to make this smaller, basically. Okay, it's not enough to completely stop the movement of potassium out. For that, you'd need to take the electrical potential difference to around negative 85 millivolts, the Nernst potential of potassium, but it does reduce it considerably. So the main result of opening this channel is that you're going to get sodium coming in. Okay, and that goes for the 5-HT3 receptors as well. The glycine receptors and the GABA A receptors are slightly different. They're anion selective, so they allow negatively charged molecules to move through, such as chloride anions, which isn't a molecule, but never mind. So chloride anions will move through the GABA A and the glycine receptors. Again, though, they'll be moving into the cell. So whether it's sodium moving in through the 5-HT3 or the nicotinic acetylcholine receptor, or chloride moving in through the GABA A glycine receptor, basically you're going to have the movement of ions into the cell. Now when they come in through this pore, the first thing they're going to arrive in is this intracellular domain. And what's going to happen? They're going to have to come out of these portals, basically. And these portals, what's brilliant about them is that they're sort of directing the ions to move parallel to the membrane. Okay, so let me explain this a bit more. If you didn't have the intracellular domain, what would happen is the ions would come in, okay, and they'd be shot off into the cytoplasm, okay, because they'd just come straight in, they'd be moving on a trajectory perpendicular to the cell membrane here, and they'd shoot off straight into the cytoplasm. Now, the advantage of having this intracellular domain is basically they come in on their trajectory perpendicular to the cell membrane, and then they'll hit the bottom of the intracellular domain, and they'll bounce out one of the portals. So their new trajectory will be parallel to the cell membrane. Okay, so that helps to keep the ions that you've moved in at the cell membrane, which is what you want, because what's the purpose of these ions? It's to change the electrical potential difference across the membrane, to alter the function of channels in the membrane. Whereas which they'll be perfectly positioned to do if they're kept nice and close to the intracellular aspect of the membrane, the inner leaflet. Whereas if they shoot off into the cytoplasm, the effect that they'll have on the electrical potential difference over here across this membrane is going to be very little, basically. So this keeps the ions that we're bringing in nice and close to the inner leaflet of the phospholipid bilayer, is the advantage of the intracellular domain. Okay, we'll continue our discussion of the intracellular domain of cis-loop ligand-gated ion channels in the next video.